All right, so here is a possibly a little bit tricksy little problem. So let's let x be an irrational number. Show that there is an integer j, which is between 1 and n, such that j times x is at most 1 over n distance to the nearest integer. So we have an irrational number, and we want to show that some multiple of it is close to an integer, in the sense that we can find an integer at most n, such that j times x is at most 1 over n from the nearest integer. How can we approach this problem? So it's possibly a little bit subtle, even to recognize what kind of techniques will help us solve this problem. But let's look for some clues. X being irrational kind of suggests that this is a number theory thing. But there are some other indications that we have a range of things here, and we want to show that one of them must meet some kind of requirement. And with a little bit of thinking, that might make you think it's possible that this is a pigeonhole problem. And indeed, basically, how are we going to show that one of these things is close to an integer? A clever use of Pigeonhole will allow us to do this basically by showing that two of these things have to be close to each other. But, so, here is, some review of the Pigeonhole principle with a nice tricky problem that will require some thinking about what are the pigeons and what are the pigeonholes. So let's start by saying that we're going to use the Pigeonhole principle. And when we're using the Pigeonhole principle, well, there's a couple different flavors of problems, but one flavor is, a straightforward classical pigeonhole, where we want to say that if we have more than n pigeons going in n pigeonholes, then there must be 2 pigeons in the same hole. And for these types of problems, the main difficulty, the main content of the problem, is to figure out what are the pigeons and what are the pigeonholes. And in this case, it's very non-obvious from the statement of the question, what are the pigeons and what are the pigeonholes? Although we should be able to see that we're considering basically all of the integers between 1 and n. We're considering the product j times x. So these things, we have n of them, and we want to show that one of them does a special thing, these are probably going to be our pigeons in some form. So more precisely, what we're really worried about is the distance from these things to the nearest integer. So let's consider the fractional part of these numbers. So the fractional part of some real number z is basically what it sounds like. It's the part that's a fraction rather than a whole number. One way to write this is it's z minus the floor of z. So for example, well, let me say, I think it's denoted, one way to denote it is with brackets z. I think this is common, but at the very least, let's use it right now. So for example, the fractional part of 3.5 is 0.5. Fractional part of, 2.76 is 0.76, et cetera, et cetera. This is the fractional part. And what we're saying is this thing should have fractional part at most, close to 0 or close to 1, basically. So let's try using this as our pigeons. What are the fractional parts of all these multiples? So let's give this a try. Pigeons. Fractional part of x, fractional part of 2x, up to fractional part of nx. So there are n pigeons. And these all lie in the interval. I guess it's open on that end. They lie in the half-open interval from 0 to 1. And if we want to find things that are at most 1 over n away from each other, you will notice that you can split up this interval into segments of 1 over n, and there are going to be n minus 1 of them. So that sounds very promising for a pigeonhole style argument. Let's consider pigeonholes, which are intervals 0 to 1 over n, 1 over n to 2 over n, and then n minus 1 over n to 1. And we have n minus 1 of these. So n minus 1 pigeonholes. So the pigeonhole principle then tells us, by pigeonhole, 2 pigeons must share a hole. And what does this mean? So there must be some numbers, 1 less than or equal to k1. Let me say there must be 2 different ones, so let me just put them in this order. Less than or equal to n, such that k1 times x and k2 times x are within, or rather the fractional parts are within 1 over n of each other. And what this means is that k2 minus k1 times x is within 1 over n of an integer namely, that integer is going to be k1 times x floor. It's going to be k2 times x floor, excuse me, minus k1 times x floor, or that plus 1, possibly. So let's illustrate this maneuver with some examples. If we take what we're saying is, if we take two real numbers, so let's say like 2.7 and 106 point something, and we're saying that their fractional parts are very close. So let's say this is 106.6. So the fractional parts are within 0.1. Then we're saying that the difference of these integers, which is what we've taken here, because this is simply k2x minus k1x, the difference of these integers, of these real numbers, rather, is very close to an integer. So close fractional parts implies that this thing is going to be very close to an integer. And let's see if I can add. I believe this is 103.9. Should be. And as you can see, these were within 0.1. So this is close to an integer. Within 0.1. And that's just an illustration of the exact maneuver you're using here to show that because these two numbers have very close fractional parts within 1 over n, then their difference is close to an integer, namely within 1 over n. And this thing, k2 minus k1, is again a number between 1 and n. So that completes the proof. And that is an example of the Pigeonhole principle. So let's review what we did here. We were presented with some problem, and we decided to attempt a pigeonhole proof of this. So then the problem is to find what are the pigeons and what are the pigeonholes. And in this case, it was quite non-obvious. But essentially the idea is that you want to make pigeonholes so that having two pigeons in the same hole gives you what you want. So without having all of this in mind, it's a little bit hard to see what the pigeonholes are. But if you're familiar with fractional parts, and I'm not going to give you a pigeonhole principle problem with things that you're not familiar with. If you're familiar with how to work with fractional parts, then you could have predicted that, I know that if you have two numbers with similar fractional parts, then their difference is very close to an integer. And so you could have said the pigeonholes should be the fractional parts of these things, because having two of those that are in the same pigeonhole will mean that we can find a number which is close to an integer. So very quickly, let's just review the other type of pigeonhole problem that you might run into. So this is the sort of generalized pigeonhole philosophy. And the way this works is you are given some setup and you want to show that, well, okay, let me give an example. So here's an example from, I believe, the practice midterm. In a string of at least 50 digits from 0 to 9, show there is a digit k that appears more than k times. So more than 2 2s or more than 9 9s, something like that. And for this style of pigeonhole, the argument is usually much more straightforward. The idea is to say, if not, then we have a upper bound on the number of times each digit can appear, and we expect to add them up and find that it's less than 50. So let's try that. If not, number of digits total is, so number of digits in our string is at most, so we can have at most 0 zeros, we can have at most 1 1s, we can have at most 2 2s, etc. We can have at most 9 9s. And if we add these all up, we find that this adds up to 45. You can do it by hand, or you could say that, you know what is the sum of numbers 1 to 9? It's 9 times 10 over 2. This is your sum of the first n numbers formula. N times n plus 1 over 2. And this, as predicted, is smaller than 50. So even if you have the max number of digits that you can get with this condition, you still don't get to 50. So if you have 50 digits, you must have one showing up more times than that. This is less than 50. So in 50 digits, must be a digit k that appears more than k times. And those are basically the main two styles of pigeonhole problems that you might see.